Hello, I'm Robert Fisher, and I'm pleased to be here virtually presenting this talk on turbulent detonation in type 1a supernovae. This is work I've done in collaboration with my colleagues Alexei Polidenko from the University of Connecticut and Vadim Gamizo from the Naval Research Laboratory, as well as some graduate students and postdocs we'll introduce later. On the right of this image, you can see the pre- and post-explosion images of a nearby galaxy that were taken in 2011. And the key thing to focus on here is the pre-explosion image showing the absence of any bright object in the same location that just after the explosion of this supernova 2011 FE is seen that basically there is no bright star at that location. This simple observation tells us a lot of important facts about the type of supernova that went off in this galaxy, which was a type 1a explosion, and that is that the star, the stellar progenitor which exploded, was very dim, most likely something like a white dwarf. And furthermore, the companion star that it would have formed with in a binary system would also have been very dim. So this leads us to some central questions. Particularly, what are the origin of the so-called normal, that is the kind of run-of-the-mill standard brightness type 1a supernovae, and also occasionally we see some very dim supernovae. These are sometimes classified as type 1a X's, and those are failed explosions. So these originate from a single channel, multiple channels, and secondly, how is a detonation initiated within the type 1a that gives rise to this explosion? So in this talk, I'll focus on two primary themes. And the first one is the physics of turbulent detonation initiation, and we're going to be focusing on the astrophysically relevant regime of an unconfined detonation, that is one without walls or barriers, obviously. And the second one is how can we incorporate that understanding of the physics of turbulent detonation initiation into full star simulations of type 1a supernovae. So to begin with, on the physics of turbulent detonation initiation, let's first think about how this can originate, this process of turbulent detonation, in a laminar flow. And Zeldovich was one of the first to give us a very kind of clear picture of how this could arise. The essential idea here is to have a gradient of the induction time or the burning time across a large length scale. This is a very kind of shallow gradient. If you think about in the situation that's depicted here, carbon burning flame, in which the flame is only perhaps 1 centimeter, the length scale is of order kilometers. And to focus on this image, there will be two plots on the same figure. On the left, temperature, and on the right, carbon abundance. And the burning front can be seen in the depletion of the carbon as it goes down to 0, and the shock front can be visualized when the temperature is increased. So a movie of what this looks like if one starts the burning at the center of this peak of the temperature gradient, the burning front and the shock front propagate down the ramp and successfully lead to a detonation. The speed of that detonation is about 10,000 kilometers per second. When you work it out, 10 kilometers in about 1,000 microseconds, and that's a typical velocity of a type 1a supernovae. Now, how does that mechanism fail? Well, that mechanism can fail if the gradient is just a little bit too too steep. If it's too steep, then what will happen is, as you can see in that image, the shock front moves ahead of the burning front and the two decouple, and it results as a failed detonation. So you can kind of develop a large suite of these simulations and understand the conditions for a successful or a failed detonation in such a geometry based on the background density and temperature. But realistic stellar environments are always turbulent, and that means that the detonation initiation is always arising in a turbulent medium. How does that happen? So to understand this, I want to first set the stage for the concept of turbulent detonation initiation based upon a basic framework that goes back to Chapman and Jouguet, and that is to look at the essential equations of mass, momentum, and energy conservation. And from these, we develop two curves in a pressure versus specific volume diagram. And this specific version of that plot I'm showing here shows the pressure on the vertical axis scaled to the pre-front pressure, and on the horizontal axis, the specific volume, that is, of course, inverse density, scaled to the original pre-front specific volume. So the 1,1 point that's shown here is simply the pre-front condition. Post-front, the Hugoniot curve, as shown here, is shifted away from that point because of the addition of enthalpy in the reaction front. And we have the division into detonations, which are supersonic burning fronts, and deflagrations. And in addition, the straight lines on this plot depict the Rayleigh lines. Those are lines of constant velocity. And 2 points specifically on this curve are those which are the tangent points drawn from the original pre-front position, 1,1. And those two velocities that originate are the Chapman-Jouguet detonation speed and the Chapman-Jouguet deflagration speed, dCj and SCj. Now, those two speeds, one of which determines the steady-state detonation speed, the second of which is a theoretical maximum for the one-dimensional deflagration front, are key velocities that originate in this problem. Now, one thing that you can ask is what happens, for instance, when you go beyond the Chapman-Jouguet velocity. The case of a detonation, that's an overdriven detonation, and typically one sees in experiments that relaxes back down to dCj. But for SCj, that velocity is a theoretical maximum. It's in Landau and Lifshitz. You can check it yourself. It's if you exceed that condition, if you move to the right, those conditions are unconditionally unstable. So that raises the question, what happens in a multidimensional flow, a turbulent flow, where that one-dimensional theoretical maximum can be exceeded because of turbulence? It's that laminar front becomes turbulent, and the burning becomes unstable, but unstable to what? And that's essentially the question that my collaborators Alexei Polidenko and Vadim Gamizov have answered. This deals with the question of turbulent burning. So this is a schematic cartoon of turbulent burning. First, here, of course, laminar burning. Laminar burning is just the balance of the energy injection with conduction across a flame front, and the laminar flame speed is shown here. The division between fuel on the right and ash on the left. Now, schematically here I've shown the presence of turbulence in eddies of all scales, and something which is most likely like Kolmogorov on large scales down to the flame scale. And this perturbs, the presence of turbulence perturbs the flame surface, and it leads to an increase of the burning by the enhancement of the surface area of the flame. In steady state burning, the turbulent flame speed is the same as the large scale velocity on the largest scale in the problem here, the integral scale, let's say L, and that obtains the integral scale velocity U prime. This is a result that goes back to Domkohler in 1940. The key thing about steady state burning, however, is that in turbulent nuclear burning or turbulent combustion in the lab, the steady state is not necessarily achieved. There are large fluctuations in time. So to kind of motivate the next part of the discussion, I'm going to show a numerical simulation that was done by Alexei Polidenko in 2011 and was elaborated upon in his science paper in 2019 that shows the deflagration to detonation transition that originates in a very strongly turbulent medium. And so this is a fully resolved depiction of combustion in a terrestrial combustion flame mixture, which is methane air. And the scale here is shown in centimeters. as the flame moves down the channel, you can see the enhancement of turbulent burning leads to greater surface area. And at some point, the burning becomes unstable to the development of shocks within the flame surface. And those shocks develop into a detonation, as you see here. When you look at the time variability of the burning rate that is shown in that simulation and other simulations that Alexei did in that paper, on the vertical axis here is the turbulent flame speed normalized to the fuel sound speed, and on the horizontal axis, time scaled to the eddy turnover time. And what you can see here is that in several cases, the Chapman-Jouguet deflagration speed, that is SCJ, is exceeded. And when that speed is exceeded, the flame becomes unstable. The burning rate increases and exceeds the Chapman-Jouguet detonation speed, DCJ. And in the case, for instance, on the left, you can see that the detonation speed is exceeded, becomes an overdriven detonation, relaxes back down to a normal detonation speed of DCJ. So why is this happening? And by the way, you can see that there are two Chapman-Jouguet speeds shown, one for the fuel, one for the product. The essential difference there is just one of the sound speed, and we'll explain why in a second. So the essential physics here is to think about a flame surface spread across some width with some flame element and some size, let's say L. There's a specific burning rate, that is energy per unit mass per unit time, that exists within that flame surface. And there's a sound crossing time for the burning to move or propagate across the surface. We'll call that T sub s. Now, the burning rate, if that burning rate becomes comparable to or exceeds the internal energy, specific internal energy, E internal, divided by the sound crossing time, that flame will become unstable. Unstable meaning that it cannot respond to hydrodynamically to the changes occurring within it. And in that paper, Alexei showed that that is equivalent to the condition that the Chapman-Jouguet speed, that the turbulent flame speed exceeds the Chapman-Jouguet deflagration speed. So that means something quite important. It means that turbulent deflagration speeds which exceed the Chapman-Jouguet deflagration speed are intrinsically unstable. That is, one does not need to achieve the detonation velocity to detonate. One only needs to exceed the Chapman-Jouguet deflagration speed. And they also showed in that same paper, in the science paper in 2019, a very nice comparison between numerical simulations and physical experiments in the laboratory in which the influence of the boundaries was minimized. So it's as best of an approximation as one can obtain for an unconfined detonation in the lab. Okay, so on to the very last part of this talk, which is incorporating this new understanding of the first principles understanding of an unconfined deflagration detonation transition into full star simulations of type 1a supernovae. The global three-dimensional simulations that I'll be presenting in a second begin with a white dwarf near the Chandrasekhar mass with some ignition point slightly offset. In some cases, we also looked at multiple ignition points. In the 3D simulations, we solved the fully coupled equations that include all the physics that's important in this problem for hydrodynamics, for self-gravity, for the reaction, and that framework has been developed over many years. In addition, there's also a turbulent flame interaction model that captures the subgrid burning. Also very important for this set of models, we characterize the Chapman-Jouguet length scale that can be derived from other fundamental parameters, including the turbulent flame, turbulent velocity, U prime on some scale L, as well as the density contrast between fuel and product, that's labeled here as alpha, and a flame stretch parameter, which is of order unity for type 1a supernovae interiors. And we characterize U prime on the length scale L using a real space calibrated operator. By the way, that L over U prime cubed is nothing more, nothing less than 1 over the turbulent dissipation for Kolmogorov turbulence. And so that is a scale invariant quantity for Kolmogorov turbulence. And so essentially you can see that the length scale that we're talking about is one which is a intrinsic length scale of the flow. So what happens? Well, I'll tell you the upshot. Whether you start with a single bubble or multiple bubble conditions, the evolution becomes very rapidly unstable to a detonation, according to this framework. Here I'm showing a single bubble initial condition. The density is shown in blue, and the second color scale shows a filter scale, which is just a few grid scales, compared to the Chapman-Jaquet scale. The question being whether the computation becomes unstable to a detonation or not. Well, in this case, for a single bubble, even at a very early time, a detonation is quite likely. But perhaps even more interestingly, if you have multiple bubbles also don't lead to a much different outcome. Normally, this would be a very vigorous deflagration according to some frameworks. And even this is unstable to a detonation quite early on. We've also looked at preliminary global 3D nucleosynthesis yields. This involves a large set of Lagrangian tracer particles, and what is shown here are the stable iron group elements in the core of this white dwarf, the nickel 56, which is shown in white, and a very small amount of intermediate mass elements. We're developing synthetic light curves and spectra, but the upshot of this is very unlikely to be a normal type 1a supernova. It's very likely to be a very bright, unusual event. So I'm going to put up the conclusion slide, and I'll take questions. Thank you very much.
Yes.
Yes. Do I correctly understand that you did large eddy stimulations?
They are effectively something like a large eddy simulation. We did include as I mentioned, this turbulence flame interaction model. So it captures the turbulence on some scale, and then there's a model for the subgrid burning that's incorporated in that model. Though I would have to say also that that doesn't really matter too much in this set of models. The subgrid burning, whether one includes it or not, the outcome is very nearly the same. That is a nearly prompt detonation in the cases that I've shown.
That's rather interesting. Most of the applications that I'm aware of are very sensitive to the turbulent reaction rate model. So that's certainly a case to be highlighted as being insensitive to that. I think you have something there that should be pointed out. Thank you.
Anyone else?
Hi, that's a very nice talk that you gave. It's a pity you can't be here in person, but
I wish I could be in Santa Barbara right now.
Well, yeah, I think you'd wish that even more if you were actually here. So, with that being said, I don't see any of your. I mean, are you dialed into the inversion mathematic physics that's been floating around the UK and stuff? In other words, what I'm suggesting, just a suggestion, strictly conjecture, somewhat speculative, that you might need less mass to have a supernova sort of condition, because I don't think you're accounting for all the energy that might be at play. That's just a suggestion.
Not all the energy, meaning
Well, if you, there's a UK grant, Alessandro, somebody in the University of Surrey is working on that. So you might want to talk to him about that, because I think that's your great presentation. I think there's a new level of energy coming down the line.
Okay, I'll take a look.
Last questions. Let's thank Robert again.